Hi, everybody. Today, we're going to talk about the basics of distributed power factor correction. And when you first start learning about power factor correction, you usually deal with one single power factor correcting capacitor if the power factor is lagging. But there's a problem with that when you have more than one load. So we're going to switch to our simulator. So here's what happens. Our system is running right now. I have two loads and I have a watt meter on each. So I have the 2 watt meter readings on the top right and the overall power reading and power factor reading on the left here. So when I engage the two loads, so I'm going to engage the first load, and we come up with 8.865 watts and a power factor of 0.58. And then when I engage the second load, I have 2.29 watts and 0.63 power factor. And that is with an overall power factor. If we look on the left, we have 11.379 watts and a power factor of 0.6, or 0.59 it says there. So what we did was, for this particular system, we have one central power factor correcting capacitor, 1.856 microfarads, and that was designed to correct the system here to 0.9 lagging. So right now we have, if we look at our scope, I put a sense resistor for IT, just so we could see that here's channel 2, this represents current. Okay, current is lagging voltage. And when we engage our power factor correcting capacitor, now we're at 0.9 overall, if we look here in the top left, and we have we've not changed power factor or power or current for either of our loads, which is the way it's supposed to work. But there's a problem with that. So if we decide to disengage one of these loads to de-energize, then your power factor changes. So now, when I turn load 1 off, load 1, now when I turn it off, my power factor is now 0.3 overall. And if you look at the scope, current is now leading voltage. So we've gone from a 0.9 lagging power factor to 0.3 leading power factor. Okay, that's a problem. And the problem stems from the fact that this capacitor's value was calculated taking into account both of these loads at the same time. So now we've overcompensated. We've turned this into a leading power factor system. Okay, so, and even if I de-energize load 2, okay, my power factor went up to 0.96, which we're still lagging, and that is because this takes up most of it. So we're still there, but there still lies the problem if we de-energize load 1. So we energize load 2, de-energize load 1, and now we've gone completely in the other direction, which is not what we want. But this is an example of centralized power factor correction. So we're going to get into distributed power factor correction, where we are going to correct each load separately. Okay? So let's move now to correct branch 1. So I'm going to switch here to paper. Okay, so we're here. So we have branch 1. So we have a 2 Henry inductor with 535 ohms of resistance. So let's just do some calculating. So the reactance of that inductor is XL1 2 pi FL1, which is equal to 753 ohms. Okay, so the Z of branch 1 is equal to R1 plus J XL1, which is 535 ohms, plus J 753 ohms, which if we calculate that and turn to polar, we have 923.71 ohms at an angle of 54.61. Okay, so if we take that, let's take the current through that branch. So the current through branch 1 will be equal to E over Z of branch 1, which is 120. We'll just write angle 0, so we're happy with that, over 923.71 at an angle of 54.61 degrees. And that gives us 129.9 milliamps at an angle of negative 54.61 degrees. Okay, so we have that. So now, if we keep working, we could say that theta is equal to 54.61 degrees. Alrighty, so S, our apparent power, is equal to E times the I of branch. So the apparent power of branch 1, is equal to E times the I of branch 1, which is 120 times 129.9 milli. Okay, and there are no angles here. So we would get, if we worked all that out, 15.588 volt amps. All right. And now the power in branch 1 would be equal to S cos theta, which is 15.588 times the cos of 54.61. And that gives us 9.02 watts. And then Q of branch 1 is equal to S sine theta, which is 15.588 times the sine of 54.61. And that is equal to 12.71 fars. Okay. Now, the fact that the angle is greater than 45 should tell us that our reactive power should have been greater than our real power. Okie dokie. So let's correct this branch only to 0.9. Let's just correct that branch to 0.9. Okay. So what we have is, put this here, lagging. And I should put that here as well. Oh, we didn't calculate the PF of branch 1. The PF of branch 1 is cos theta, which is 0.58 lagging. Okay, so we want to correct that to 0.9 lagging. So 0.9 lagging tells us that, so we know PF is equal to 0.9 lagging. And we know that P is equal to P of branch 1 is equal to 9.02 watts. That does not change. Okay, so we just carry that number. The true power does not change. Alrighty, so our new apparent power is equal to power divided by power factor, P over PF, which is 9.02 divided by 0.9, which gives us 10.05 volt amps. All right. Now we can figure out a new Q. Our new reactive power in this corrected branch would be S with a power factor of 0.9. Theta would be equal to the inverse cos of power factor, which is 25.84 degrees. Okay, so Q now is equal to S sine theta, which works out to 4.38 VARs. Okay, so what we need now is a capacitor. We need a capacitor that is going to decrease our total reactive power of this branch from 12.71 VARs down to 4.38 VARs. Okay, so we need a capacitor that will result in that reactive power. So the reactive power of our capacitor, QC, would be equal to 12.71 minus 4.38. So just to remind you where those numbers are coming from, is the 12.71 is coming from there, okay, all the way through, and the 4.38 is coming from here. So we have our new reactive power, our original reactive power, and this capacitor is being tasked with bringing that reactive power down. So 12.71 minus 4.38 is 8.33. Okay, so 8.33 is the reactive power of that capacitor. So now, in order to find the capacitance, we need to go from here. We'll find XC, the reactance of that capacitor, and then we'll find the capacitance. So it's QC. So now XC is equal to E squared over QC, which works out to 1.729 K, and that is the reactance of that new capacitor. So to find the actual capacitor value, the capacitor would be 1 over 2 pi F XC. And when you go through on your calculator, you end up with 1.534 microfarads. Okay, so that's what we end up with. So does that work? So let's remember this number right here. All right, let's remember that number. I don't have to remember it because I just have to look down at my sheet. So 1.534. So let's go back to multisim. Okie dokie. So we're back here. I'm just going to get rid of the scope just for a second. It's getting in the way. And so we're there now. So we need to put a 1.534 microfarad capacitor across this load. So let's put that in there. Capacitor there. Four micro. We're here. Okay, so let's watch the power meter, the watt meter on branch 1. I'm going to disengage that. So now, branch 1, the watt meter's right here, okay, has now been corrected to 0.9. So that branch is corrected now. Okay? The branch is corrected. So now let's correct branch 2. All right? So we're going to go back to our sheet. So if we remember branch 2, it was 8 henries in series with 2.45K. All right, so I just redrew that there for reference. So let's figure out, first we have to figure out XL2, the reactance of L2. So XL2 equals 2 pi FL2, which works out to 3.016K. All right, that's what we have there. Now, the impedance of that branch, Z of branch 2, is equal to R2 plus JXL2, which works out to 2.45 kiloohms plus J 3.016 kiloohms. All right, that's what we have there. And then if we convert that to polar, we have 3.885K at an angle of 50.91 degrees. So that's what we have there. So if we were to calculate everything else now, IT, or I of branch 2, sorry, is equal to E over impedance of branch 2. And that works out to 120, angle 0 again, over 3.885K, angle 50.91. And that works out to 30.89 milliamps at an angle of negative 50.91 degrees. All right. So let's start getting all of our power values. So the power factor of branch 2 without correction is 0.63. And we got that by doing cos theta, which was cos of 50.91. Okay, and that equals 0.63 lagging. All right, that's what we have there. Now, the apparent power of branch 2 is equal to E times the I of branch 2, which worked out to 3.761 volt amps. All right. Power of branch 2 is equal to S cos theta, which is equal to 3.761 times the cos of 50.91 degrees, which worked out to 2.34 watts. And then the reactive power before correction is S sine theta, which is 3.761 times the sine of 50.91. And that worked out to 2.919 VARs. All right. So that's stuff that you would have been doing as you were performing all kinds of power calculations. So let's correct branch 2. So PF power factor equals 0.9 lagging. All right. So what do we know here? Well, we know that power factor is now equal to 0.9. So that means we know theta is equal to inverse cos of power factor, which works out to 25.84 degrees. Okay. All right. And we know that power is equal to 2.34 watts. That hasn't changed. Okay. And we got that from here. All right. That carries forward. So now we need to figure out the capacitor. So we can do it the same way we did with the first branch. We can figure out our apparent power. So S is equal to P over PF, which works out to 2.34 over 0.9, which worked out to 2.6 volt amps. All right. And then Q was equal to S sine theta, which is 2.6 times the sine of 25.84 degrees. And that Q worked out to 1.13 VARs. Okay? So what we needed then was, or is, we need a capacitor that will decrease our overall reactive power from 2.919 down to 1.3. Okay? So we would say that QC, the reactive power of the capacitor that we need, would be 2.919 minus 1.13. So again, we got those numbers from here. The first number comes here, and we'll make our way down there. And this number, we just calculated. Okay? So if we do that, we would end up with we would end up with 2.919 minus 1.13, and we get 1.789 VARs. 1.789 VARs. Okay? So we know that. So now we can figure out the reactance of that capacitor, so we can work towards the actual capacitor value. So XC would equal E squared over QC, which is 120 squared over 1.789. And that would equal, if we did that, 120 squared divided by 1.789. Okay. So if we want to throw that on there, and we end up with 8.049 K. All right. So now we can figure out the capacitor value. That C, the actual value of C is 1 over 2 pi FXC, which works out to 1 over 2 pi 60 for frequency, and XC is 8.049 K. And we end up with 1 divided by 2 divided by pi divided by 60 divided by the answer. And we get 329.546 nanofarads. So I'm just going to say 330 nanofarads. All right, gang? So 330 nanofarads. So let's go back to multisim, because we love multisim so much. Nice. So we're here. So let's put in a 330 nanofarad capacitor across the second load, the second branch. All right. We have this. Let's connect it in parallel to the load. The entire load, not just the coil. And then 330 nano. There we go. All right. So both loads are disengaged right now. So let's start the circuit. We energize the circuit. So when we energize load 1, we look here. We have 8.863 watts and a power factor of 0.9. And our overall power factor is 0.9. Okay? And then when we energize the second load, the power factor of the second load is 0.9. And our overall power factor is 0.9. So we don't need this anymore. Okay, we don't need that. So you can see we still have that. And the other thing you'll notice is that these two capacitors right now, when the load is engaged, both loads are engaged, these two capacitors are effectively in parallel, okay? They have a direct connection here, and they have a direct connection there. And we know that if we add parallel capacitors, we just add the capacitance, and that's what happens here. If you added these two together, you would get 1.864 microfarads. So we're fairly close to what we needed to correct the whole thing. The only thing is this way with distributed power factor correction, we are only correcting what requires to be corrected instead of having this across the whole thing. All right, so if we had 5 loads, we would have 5 power factor correcting components. All right, so I hope that made some sense. If you have any questions, just let me know. And thanks for watching. You don't get this kind of entertainment on Netflix.